Years ago, horses and oxen played a major role as the power for both agriculture and industry. When the lands of North America were first settled, it was animal power that carried the pioneers through this unknown country. The power of the horse, the mule, and oxen broke the land, hauled the logs from the forests, and pulled the cedars, supplying the homesteaders with many of their needs. But by the end of the 19th century, there had been many developments that would, in the decades following, alter many of the long-standing traditions of rural and agricultural life. In comparison with the centuries of real horsepower, the evolvement of this new mechanical era saw many changes and in a short time. The steam engine, as formidable as it was in both its weight, appearance and ability, was soon replaced by smaller tractors, and so playing a major role in farming for a moderately short period of time. But as short a time as it was, the magic of the threshing crews and these massive steel horses remains an important part of our rural history. The onset of steam power offered many options that would have been quite limited without the steady power of the pulley and the belt. In many areas, this steam power allows sawmills to run without the need of water wheels. Some of the smaller portable mills traveled the countryside, working in areas of greatest need. Thrashing crews harvested the fields of grain, large ploughs turned over the sod and stubble, and hay presses began to take the place of the straw stacks. It was a new era in the countryside and of changing ways of farming. As the power of the smaller tractor developed and became more economical for individual farmers to own, the popularity of the steam engine began to fade. Many of these engines were sold for scrap and lost for the appreciation of future generations, whilst others were left in hedges and barns, on the side of fields and the back corners of farmyards. By the early 1950s, some steam enthusiasts were starting to gather up some of these engines and old equipment. And before too long, these efforts and dreams led to the beginnings of some of the fine museums that exist today.
Yes, well, this museum is the result of one man's effort in the very beginning, who back in the late 40s and early 50s and all through the 50s and into the 60s worked very, very hard gathering machinery, gathering firstly steam engines and old tractors, and then of course the implements that they used them with came along as well. His name was Donald E. Carruthers, and he dedicated his life to the establishment of this museum. It started out as a collection, and then when his father saw what he was doing and the effort that he was putting into it, his father donated a few acres of land first on this particular property, and in later years a bigger portion of the land, and then in the final analysis he donated the whole half section, 320 acres, to his son's efforts, and this is where the museum is housed today. We have lots of room at this point in history. There was a lot of fellows that went along with Don in the early days and helped him to get it established, and this is our 40th show. 39 years ago they started this little thrashing bee, which has developed into what we see today. We count on crowds of maybe 70,000 people in the 4 days, and we have something for everybody, we feel. The steam engines and the gas tractors and cars, and then on the ladies' side there's cooking and the baking and the fashion show, and we have a playground for the children. The museum is a very varied thing, and we feel we offer something for everybody that come here, and you can't see it all in one day. Part of our show each year is a focused feature on some particular aspect of the museum. It began in 1989 with the J.I. Case Heritage Expo. Each year we have a different focus. We focused one year on the Ford family of fine cars, then there was a General Motors, animal power, whatever, and this year in particular is the stationary engines, stationary engine display that we see behind us in the background. We feel that we have a brand new bunch of volunteers every year when we have a different article that we focus on, and it helps our show immensely. It has become a very important part of our show and is also a great revenue gainer.
The history of Western agriculture has been well preserved by many of the museums that are found across the Canadian prairie provinces. The actual workings of the equipment and the old ways of life are preserved through the interest of the folk that make up the manpower behind the scenes. These men and women are involved with the events of the day, helping to run the many restored and running implements and machines that depict the farming era in the early part of the century. It is only through their efforts that we are able to visit and indulge in the past. July in Austin is a truly busy time. It really is one of the finest examples of our living rural history on the prairies. The recreation of a small village with original stores, shops and other turn-of-the-century buildings sets the stage for the experience of this four-day event. For so many of the visitors at these steam events, the size and ability of these machines is quite inspiring. But their actual workings, the process of converting fire, water and steam into functional and efficient horsepower, still remains a total mystery. As the steam engine played such an important part in the beginnings of this mechanical and agricultural evolution, an explanation as to the workings of these engines would be of some interest.
I'm going to give you a little walk around here at the grounds of the Austin Manitoba Agricultural Museum. The engines lined up in here are built somewhere around the 1900s up into the 1920s, although we have an earlier portable that is over on the planing mill right now. Some of the features on these engines: this is a single cylinder case. There's a locomotive style boiler, which means that the firebox is mounted at the rear here, and there's approximately 2.5 to 3 inches of water on all sides, from the throat sheet to the rear sheet and the side. Heat is picked up, and then through the barrel we have a number of tubes, and each tube, if it were rolled out, would have approximately 4 feet of heating surface. We'll take a look inside the barrel here. And engines will run anywhere from about 32 to 92 tubes. Some of them are 1 inch, and some of them go all the way up to 2.5 inches, depending upon the manufacturer. That's okay, I'm going to go back in. The boiler has a number of key safety features. This water glass here gives the engineer an indication of just how much water there is in the boiler, but we also have what are called tricocks. There may be 2 or 3 of these, and you can by opening them, get a direct reading as to whether you have water or steam. Steam will come out clear, water will come out white when you're under pressure. On the top of the dome, if we move over this way, on the top of the dome, there is a safety valve, and that is set by the boiler inspector, who is satisfied at a particular safe operating pressure. When these machines were designed, they had a 6-to-1 safety factor. So if an engine was running at 150 pounds per square inch, it meant that its boiler design could handle 6 times that pressure. So they are an extremely well-built boiler in its day. We'll take a look at some of the other features. The firebox here will contain our fire. We control the temperature with the damper. There's a damper control with all of the engines, and we maintain our water level with the injector. Some of the machines have mechanical pumps that operate while the engine is running and will feed water in on a steady basis. When you're working under load, you would steady feed the water, either from the injector or from the pump. If you're plowing, you want to have a steady trickle going into the boiler to restore the lost steam. So you maintain your water level, you maintain your fire by a steady firing also. The boiler produces steam, and the steam is collected in this dome because we want steam as opposed to water. It won't compress. You can actually blow the head right off the engine with water. So we collect the dry steam in the dome past our main valve, and when the engineer opens the throttle here, the steam passes forward through the main line to the governor and then down into the steam chest. Now we'll just rotate the flywheel. As the crosshead moves back and forward, in behind it here, there's a valve rod, which is tied in on an eccentric on the crank. And as that valve rod moves back, it will introduce steam into the front end of the cylinder and push the piston back. When it does that, the valve rod, at the same time this crosshead is coming back, opens the port so steam can be introduced and push the piston the other way. And from the crosshead, there's a crank that changes the reciprocating motion here into rotary motion. And then once the valve rod reaches its throw, it turns back again and introduces steam to the back of the piston and pushes it forward, so that you have power at both ends of the piston all the way through. This governor comes into play when you're operating at high speed. The flywheel is designed to turn between 225 and 250 RPM, depending on the type of engine, but most of them are within that range. In order to keep that, the governor here has little fly balls which will swing out at speed and push this pin down inside the globe where there's a disc, and it'll shut the steam off if the engine is revving too high. And as the engine slows down, the balls come back in and the pin lifts up and introduces more steam, so the engine picks up more speed. And that's rather important if you were thrashing or if you were plowing and a belt or a chain let go. It prevents the engine from over-revving. An engineer couldn't respond fast enough to shut the throttle down. So it's a very, very important piece. Locomotives don't have this because their sheer weight is a speed control in itself. This is a lubricator. We use a special lubricant, steam cylinder oil, and that is injected normally into the throttle body and passes in through the governor to the steam chest to the cylinder to lubricate all of the key components in there. That steam cylinder oil doesn't wash off. It has particular properties that won't wash off under pressure or underwater. To use mineral oil in there would be simply to destroy this entire machine. In the earliest days, they used an animal oil that was hydrogenated, and today oil companies have produced a synthetic product that has those properties, although some of the old engineers don't agree with the feel of the stuff. It's supposed to do the same thing. This model is a 65 case that we're standing beside in this line of engines here. The 65 was probably the most popular of the farm engines because it was small enough that it didn't require a huge outlay in terms of cost, and at the same time it was large enough to do plowing and thrashing. It was a good size, a general purpose engine, extremely popular. There were many thousands of these that were constructed. There were heavier engines that were constructed, and we can walk down the line. This engine, also made by Case, has extension rims on it, which increased its capacity for pulling. And this was a popular engine for plowing, breaking the sod. The 110, which has a cab, you'll see that later, was an exceptional braking engine, good for plowing. You can see up here a ham lamp. I'll close this door here so that we can see it a little better. This was used in the evenings when the threshing crew moved from one farm to another. A custom thrashing unit would move at night, and it would literally be a train. You'd have the engine, and behind that the water tender and the coal bunker, and behind that the separator, and behind that the bunk car. And it would trundle down the road. And this ham lamp has a very interesting feature. The wick is much like a sock. It's a round wick, but it cast enough light down the road that it allowed them to move safely. Bridges were always a problem in the early days, and there was more than one engine managed to make it through and break a few timbers on the way. They're extremely heavy. Most of these engines will range from approximately 8 ton to 24 ton. So there's a lot of mass to move. These engines move at about 1.5 miles an hour. Some of the engines, like the Avery undermount, had 2 speeds, a road gear and a plowing gear, but most all of these engines simply had the single gear. It was cheaper, there was less maintenance work involved. Now we can move to the engine over here, which is a double. This engine has 2 cylinders. You can see the 2 round discs just behind the dome. And each one of those cylinders, it's like two simple engines mounted together. But what it does is it allows you to have twice as many compressions on the same rotation, so that instead of having power simply forward and back on a single, you've got four actions taking place. The power delivery is smoother. Doubles were more popular on sawmills. Sawmill engines required a very smooth delivery, and what happened is that the belt wouldn't get a standing wave, which you get on a single. What you would get is a steadier belt delivering to the saw. For the farmer, though, there were twice as many links to maintain and twice as many pieces to lubricate, so the double was not as popular as a farm engine. water for the engine is located on, depending on the type. On the side we have here two large tanks with crossover pipe. The Minneapolis engines and a number of others, the tank was located up over top of the smoke box. The case engines had the water tank with the operator standing atop it, and this area right above the drawbar area would be holding the water, and some of the tanks go up to 450 gallons. The water glass is located in different places on different engines. On the Nichols and Shepard here, it's a rear mount. The Waterloo engine also has a rear-mounted water glass, and so too are the tricoques here, also located on the rear. These are very conveniently located, since you have to walk around on the side for a case engine. But in the event that a water glass breaks, it's very hot, and getting scalded is part of the risk that you take when you're operating. But there are procedures for managing to shut down safely. The steam engine became a steam traction engine somewhere in the late 1890s. Portables were steam engines that were hauled by horses. But once the traction engine came in, the feature was that there was a clutch, and all that is a friction fit. There's a block of wood that is jammed against the pulley and allows the gears to be engaged and to drive by the main wheels. And steering was accomplished by a worm. The steering wheel located up top has a worm here, and by rotating that, you lengthen and shorten the chain, which will turn the wheels. It takes a lot of turns, a lot of hard work, and the steering is always just a little bit sloppy, and it takes some getting used to. It's much like steering a boat, only you have to crank an awful lot. The 110 case has a power steering feature, and by simply moving a lever forward or backwards, engages a clutch by sliding sideways into a set of cones and drives a bevel gear which turns this shaft. And by shifting the cone the other way, you engage the bevel gear and the steering worm turns the other way. One of the things that steam engines do is send up a shower of sparks. You don't see that very much by day, but in the evening you can see a shower heading up. And it was not uncommon to be able to start straw fires in the fall. So a number of different kinds of smoke or spark arresters were created. This one that sits on the back of this smokestack is cone-shaped, and by lifting that handle, the rod can be turned and the smoke arrestor dropped, or spark arrestor rather, dropped inside. On the Nichols, we have a spark arrestor which is bolted right onto the top of the smokestack. There's a little cap that can be rotated down. We have ours open right now, since it's not really a fire problem, and it does provide a bit of a damper when you are trying to fire up. On the George White, which is just ahead of us here, it's something almost like a top hat, but it performs the same function, and that's reducing the number of sparks that were sent into the air. Now, Rod Durham is cleaning the flues on his Rumley here. The soot buildup inside those flues acts as an insulator, and it's rather important to have clean tubes. It's much less work in terms of firing, it's more fuel efficient, and the engine will respond more quickly when you need to work it hard. But cleaning flues, as you can see, is hard work. These are the kinds of things that the crowd misses when they see a steam engine go by. There were dozens of different engine manufacturers. This George White was manufactured in two places in Canada, in Brandon, which is only 45 minutes west of here, and in London, Ontario. The case engine was built in Racine, Wisconsin. Railways would bring these machines into various parts of the country. The Rumley came from LaPorte, Indiana. All of these engines were largely shipped by rail. The owners were oftentimes obliged to do custom thrashing because of their cost. An engine like this might cost $3,500. And back in the early 1900s, when wages, I know for my grandfather, were 25 cents an hour, $3,500 is an awful lot of money. So custom thrashing was in the order of the day. And a lot of these units would actually thrash right into December, so that they'd simply move from farm to farm, and even though there was snow and cold weather, the engines were kept hot right through the day and right through the night, so that the thrashing could continue until everything was done. It was a high labor-intensive kind of work, and labor-intensive, you would have to have a fireman, you'd have to have an engineer, somebody who was charged with securing water, someone who was charged with securing either coal or wood from the wood lots on the farms. There was the separator man, the spike pitchers, all the people who were involved in the operation with the horses to bring the racks to the separator where they could be offloaded and the grain thrashed. So crews of 24 were not uncommon. The farm wife is the unsung hero because she had to feed all those men. The ladies worked very, very hard. These are the kind of glory jobs that we get, but they are the unsung heroes. And come lunchtime, I appreciate them still.
In the early days of steam, only a few of the engines were self-propelled. The large stationary steam engines traveled by horsepower between jobs. As the traction engine came into existence under its own power, the inconvenience of the stationary engine led to its decrease in popularity and use on many of the farms. Their actual operation of producing steam and creating power was much the same as with their larger cousins, the self-propelled traction engine. Their reliability as a stationary power source remained popular, operating sawmills and in other stationary work where minimal moving was required.
I'm running a 1907 10 by 10 cylinder 20 horsepower case. It's running an edger. The engine itself is the originality of it is unknown. It's what they call a 20 horse portable pulled by 4 horse hitch. It was mainly used for thrashing. The engine itself is 1907, and the portables were a lot less money at that time than a traction engine, which would be able to pull itself. Mainly a traction engine would be used for plowing and thrashing as well, but it also broke the sod in here in the prairies. Portables were a lot cheaper. This portable would probably cost around $1,500 at the time. A traction engine at this size would cost close to $1,800, and the J.I. Case company gave a 5% discount for cash customers. They were made in Racine, Wisconsin. They also made thrash machines and road construction equipment. They have in the late 20s, J.I. Case at that time stopped making steam engines in 1924, and they had a total of 35,000 engines. The traction engine, the last known serial number plate was 35,550, I believe. At that time, the steam era was just about ending, and most of the engines ended up in sawmill sites, or they were scrapped during the Second World War for the war effort. The Case company stopped making them in 24, like I mentioned. This particular engine, being saved from the war effort, Could have ended up in a sawmill site running an edger and a planer. It wasn't big enough to run the sawmill, but it was probably large enough to run the accessories for the mill. Edger, planer, and a cutoff saw. It's used to supply lumber in the Riding Mountains. When these engines were made, shortly before the First World War, the logos on a lot of companies was to feed the world, and so there was quite a demand for good grain, and the United States and Canada were the only ones that really could provide that grain for the rest of the world. That's when farming was good. When the steam era was big, the person that used to fire the engines was usually up first, and he would have to feed the horses for the thrashing crew, plus he would also have to light the fire in the engine. And in those days, if you weren't close to any wood, you burnt straw, so you had to steam up fairly quick, and you had to haul the water from dugouts in barrels, and that was all put in barrels by a hand pump. Firing the engine, it took a lot of work. You were up at 4 in the morning in those days, and you didn't quit till the sun went down. Firing the engine takes quite a bit of work. You got to have good wood. Also, you got to have good water. Many an engine were destroyed through to bad water. The water level in the boiler has to be maintained at a proper, safe operating level. Too much water, it'll end up priming the engine, which means water's lifting out of the boiler into the engine. Also, too hot a fire, the relief valve on the boiler will let go, and you're wasting steam and also your fuel for that. Keep the flues clean. You got to scrape them every morning. That way you're using your fuel more efficiently. While the fire is going and getting your water hot for steam, a lot of engineers do a grease job. They oil their engine, check for any water leaks at all, maybe tighten the valve packing here and there. Cleaning the grates and the ash pan out every morning is a good practice. There's also a job that you have to maintain is safety, and that's one of the biggest things that we have to make sure that we have a safe engine.
With the onset of steam power, equipment developed to make efficient use of this power. With different situations and requirements in agriculture in different parts of the world, some of the machinery developed in quite distinctive ways. One of the most obvious differences was the methods of ploughing in Europe being so totally different from that of the plains of North America. In most cases, the engine power of the British traction engine was somewhat less than its American counterpart. Because of this, the power for ploughing in Britain was reserved totally for the plough, rather than the increased job of hauling the many tons of actual engine across the field as well. And much of this work was completed through the fall and winter, and unlike the dry and flat farms of the grain belt, the wet conditions and the hilly countryside of Britain created greater problems in achieving sufficient traction to haul a plough of any size. But steam ploughing was a major part of the work of these engines, with contracting crews managing a significant part of the work of ploughing the fields of Britain in the early 1900s. As a ploughing crew required 2 engines to tow the plough back and forth across the field, these engines were often sold in pairs. Some of these pairs still remain today, although in many cases the engines that work as a team now may well be quite different.
This is a Fowler ploughing engine built by Fowlers of Leeds in 1918. She was supplied one of a pair to an agricultural contractor, which was, when they say contractor, he would go around for other farmers ploughing. To have been one of a pair, supplied with a cultivator, water cart and living van, and it would have cost in 1918 £3,000. She was purchased originally by the Ministry of Defence for food production for the troops in the 1914-18 war, He later went to the contracting firm Bomfords and Carr, where she worked until the late 30s, when she was made redundant and stood derelict until 1967, when she was bought by enthusiasts from Bristol, who totally rebuilt her over 6 years, replacing the firebox, the inner firebox, all the boiler tubes, and a lot of the motion work had to be repaired. She weighs 18 tons. She carries on her winching drum 440 yards of winching cable, which is driven by the engine. Two engines would cover about 30 acres a day and consume 800 weight of coal and up to 500 gallons of water a day. The other engine on the other end of the cable is a Fowler single. She was built in 1870 by John Fowlers of Leeds. When I say a single, she's a single cylinder slide valve. This is 2 cylinders of a compound configuration. She is one of the oldest working engines in this country at the present time. She weighs 22 tons. She also has 440 yards of steel winching cable, and we've got the pair connected up together across the field to a plough, what they call an anti-balance plough, which is pulled across the field one way, and then by the steersman on the plough would be tipped and pulled back again. The plough, when we purchased it, was missing moldboards and shears, which we've since replaced. We can't age the plough. We are very confident that she is definitely over 120 years old.
The ploughs themselves differed depending on what area of Britain they were to be used. The fenlands of eastern England have very deep soils, and so would be ploughed to a greater depth. The heavy soils, with their clay base and shallower topsoil depths, may have required a lesser ploughing depth of around 6 to 8 inches. In total contrast, the chalk downlands with their shallow topsoils had to be ploughed with great care and were rarely turned over at all until the demands of the war rations in the First and Second World Wars.
Oh, they first started ploughing this team, I suppose, about 1850, but not quite like you see it today, a different system, which is no longer, nobody's got one of those. But this sort of developed towards the end of the 1890s and went right on up to the 1930s, which basically is 2 engines, one each end, pulling the plough, or cultivator, or whatever it happened to be. That plough, most of these engines are all made by Fowlers now, though we have one exception, which is in another part of the field. But all the implements are made by Fowlers. This one probably was a fenland plough, because it's quite a deep digging plough. We've got to be a bit careful here that we don't plough the field too deep and make it look white with all the chalk. But there's several variants of ploughs about, of which every one here is different to the other one. This one is a 4-furrow deep digger. It takes a fair bit of pulling, and you'll see it in a minute when they set off. It's only probably about half its depth that it was designed to do, but the old farmer will go a bit mad if we make his field look the wrong colour. Well, if you compare England to Canada, I suppose England was a little bit late in getting biggish tractors to pull trail ploughs, and this really replaced the horse more than anything else. Of course, it's what could be done in a day with this compared to a horse is quite phenomenal. So I suppose that's why this system caught on well. And of course in Canada you might have 2-mile long fields, which is a bit of an embarrassment for these. the ropes on these engines are roughly 600 or 700 yards long, so you can only do that length of field. It becomes a bit difficult to do it anymore. Most fields cover that. We're only using about 3 parts of rope here today. You can see it goes a fair way, but I think that's the reason why steam ploughing really took off in England, and it did go a lot abroad as well, but I would not have thought much went to Canada or indeed America as a whole. It mostly went to Africa and India and places like that. Yeah, all these ploughs were designed to the farmer or contractor who owned them to suit the areas they operated in. They're no longer in those areas, of course, but yes, you'll get fenland ploughs and heavy land ploughs, and they are all different. This is, I might have said, is a fenland plough because the topsoil up in the fens is feet deep, so it doesn't matter. But that would be useless on a heavy bit of land because you would bury the topsoil and never see it again. So the ploughs were designed to the needs of the area they were destined for originally. But of course, in preservation, this plough I think always worked in Lincolnshire till we've acquired it, and now it has to go wherever we go on these sort of demonstrations. But it's not entirely suited to this Dorset land, really. The plough has to be steered because it will. You might not think it, but it will not go in a straight line. Although it's been pulled by a wire rope, it will go in all directions. So you have to have a steersman on it, as you do all these implements, whether it's a plough or a cultivator. And that is the steer. I mean, it is the steersman really of the plough who makes the ploughing either look good or not so good, rather than the engine driver. And when he's on there, that'll steer conventionally as you would a car. You turn right hand down and you go right, but going the other way, it's the other way about, and that gets a bit confusing. But it sort of comes to it, and it is the bloke on the plough who really makes or breaks the job in a way, and the engine driver's only pulling it. In commercial days there would have only been one, or perhaps the cook boy might have had a ride on it, and you had to be a bit on the strong side, but we're cheating a bit now. You would not have had a gang like you've seen go up and down here on it, really. Usually the steersman and the engine driver would have to leap off the other end and give him a hand to pull it down if that was necessary. But we're all joyriding about on it, really. But commercially, you wouldn't have had any more than one man on it. 3 men, probably, one on each engine and one on the plough.
Okay.
In contrast to the cable ploughing found throughout the British Isles, the actual method of ploughing in North America and the equipment used was quite different. These large and heavy steam engines hauled ploughs with as many as 12 moorboards. Men were required to stand on the platforms of the ploughs to operate the levers that raised and lowered the moorboards at each end of the field. This system was quite ideal for the large fields of the western grain belt, and also suited the West's dry and flat conditions. The smaller fields in Britain would have been a limiting factor with the turning area required for these engines and their ploughs. On the prairies, this proved to be no problem.
Young ploughboy, come listen to this refrain, and join with me in chorus to sing the ploughboy's praise. My song is of the ploughboy's praise, and unto you I relate the same. He whistles, sings, and drives his plough, the brave ploughboy. So early in the morning, the ploughboy he is seen, all hastening to his stable, in his horses for to clean. Their manes and tails he does coat straight,
with chaff and corn he does them bait.
and he'll endeavour to plough straight, the brave ploughboy. When he goes out in the morning to harrow, plough or sow, and with a gentle cast, my boys, he'll give his corn a throw. All this I'll have you understand,
It's just to fill the reaper's hand.
likewise I'll have you understand, it comes from the ploughboy. Now seed time being over, the fields look fresh and gay. There's merry lads to mow the grass, while damsels make the hay. The small birds sing on every tree,
The cuckoo joins sweet harmony.
all welcome here as you may see, the brave ploughboy. Then haying being over and harvest does draw near, our master he does welcome us with plenty of beef and beer. We all sit round to drink our beer,
While peace and plenty fills the year.
and we'll be merry while we are here, and drink to the ploughboy. Now harvest being over, we start the plough once more. Our master has invited us, unlocks his cellar door. With cake and ale we have our fill,
Because we've done our work so well.
and there's no one can despise the skill of the brave ploughboy.
Although much of the equipment in this era was being developed for mechanical operation, there were still some areas that were progressing for the use of horses. Some of the earlier balers, or hay presses as they were called, were designed to be used with horses. The demonstrations at Austin this year included 2 different horse-powered hay presses with totally different drive mechanisms. 4 horses powered the gear and belt-driven press, while only 2 horses were required for the horsepower system, as it was called. The John Deere hay press was actually designed for use with a tractor, although the bevel drive mechanism, which was designed for horsepower, was quite suitable for the many different types of equipment, such as a small wood saw and mill, a grinder, and even a small thrashing machine. To drive some of the larger equipment, as many as 12 horses would have been used to drive the belt. Some of the earliest of these horse-powered systems date back to the mid-1800s. The press, driven by the eccentric plunger, was built in the United States at the turn of the century. This hay press was bought used by the Barron family in 1927 when they farmed in Saskatchewan, and it's still owned today by Howard Barron. These systems were seldom used for baling hay or straw for on-farm use. Rather, they were mostly used for an outside market and for shipping out. On the Barron farm, feed was pressed into bales weighing around about 100 pounds and then shipped by train to livery stables in Regina and Saskatoon. At that time, there was a strong market for good feed for the many teams of dray horses that were used in the cities. The 1930s were also times when drought caused drastic shortages of feed in certain areas. The Barron family managed to custom press many hundreds of tons of feed for different farmers and businesses. Most of the work was done in the winter, forking the hay and straw from the stacks that were made at harvest time. This meant that the press could be operated for long hours each day, starting with one team as early as 8 in the morning. This team would work through till noon, when a fresh team would be hitched up for the afternoon session, ending up at about 5 or 6 in the evening. At that time, the cost for custom pressing was $1 a ton, with the farmer supplying the wire for tying the bales. This press was last used by the Barron family in 1942. In contrast to the use of these small presses, there was a greater interest in baling up much of the straw and feed in Britain. The wet climate of the British Isles meant that, unlike the dry grain belt of North America, one way or another the stacks and ricks on the farms of Britain had to be covered. The barns and storage areas for this bulky material was far more efficiently used once it had been pressed into compact bales, and manpower was quite abundant in rural Britain in those days. Mostly, these hay presses were belt-driven using the power of a tractor or a steam engine. With this new revolution in agriculture, these mechanized farming practices meant that farming itself became more intensive. The larger acres of crop land meant that more livestock could be handled, which meant more barns and sheds had to be built. And as the pioneers settled the vast lands of North America, there was a growing need for building materials. By the turn of the century, and with their modest prosperity, these farmers began to build more substantial homes and farm buildings. And once again the requirement for lumber continued to increase. Up until this time, water and wind had been the power source for many of the lumber storing mills, but the power of steam gave a new dimension to these mills. In Britain, the portable saw bench offered a far greater flexibility. In the new settlements of North America, where water sources were sometimes quite limited, steam power became the strength behind much of the lumber that built the West. But like much of this machinery that was developing, these benches were all quite different.
Now I've been in timber all my life, but going back before my time, the method of converting timber was by hand using a pit saw, a long hand saw. Well then, the circular saw came into being, powered by a water wheel, windmill, and then the advent of the steam engine. There's an example over there of a portable steam engine, not a traction engine, an engine on 4 wheels. That was the forerunner. By this time, saw benches are becoming more sophisticated. This blade here is an ordinary solid tooth blade. The other ones, some of them have got chisel tooth blades, which were an American patent. This one has to be set. The other ones are a chisel tooth, no setting, no maintenance, just sharpening. This saw bench is made completely of wood. It's a lovely little bench, made in Scotland. The other ones are wooden frames and steel parts. There's one here somewhere, all steel, steel frame, steel rollers, everything steel. But they've all got their good points, but myself, being a Tiverton chap, I've got a soft spot for the Stenner bench. Joe Stenner, the originator of the business, he started in Tiverton in 1870, making saw benches and general equipment, and his design, which is the one I'm working on there, his design of 1890, it still continued until 1935 with hardly any modifications at all, which shows and proves the wisdom of his first design. It's a beautiful machine, and it's still a good machine today, even to earn your living by. I've had 40 years on the road with one of those machines, going around to farms, and it's still good. I would say this one here could be around about 1920. It's a job to tell because these were a light-made bench for small stuff. Their main job was resawing timber, which was unloaded from vessels coming from Canada. The timber used to come over in blocks about 12 inches square, and it was resawed on this light bench. But this one here has been travelled with an old gentleman. He died here last year, actually, at the age of 86. But he travelled with this bench to every show here. That's 25 years. It's a lovely thing. He's been to Holland with it. He's been to Ireland, and it comes here every year. The main difference is these rollers here are cut out of a solid piece of wood with a metal bar going right through. The bench that I'm working on there has a steel table and steel rollers as against a wooden table here. It makes a very, very light and easily constructed machine, which is still very, very useful. Well, this machine here is what they call the Stenner number 2. Stenner's made 4 or 5 different benches. Number 1 had a 12-foot table. Number 2, which is this, had a 20-foot table. Number 3 was a 22. Number 4, which is that one over there, had a 24-foot table. They then made one even longer, a 30-foot table, with tables joined in the middle, and you could separate them if you just wanted to use a 15-foot plate for short work. But there's so many little things which Stenner incorporated in this machine. You've got plenty of room here for a heavy loading skid to be put up without coming in the way of the table. And you've got a nice wide table this side to carry the big log. You've got a nice wide narrow table, and this very interesting, the self-feed gear on this one. The self-feed drive, that is the drive that carries the table up and down. There's 4 speeds. It's driven from the slap pulley, so that when your saw is stopped, you can still operate your table without the saw being put in action. It drives from here down to the gearbox, and you've got four belts which are tightened underneath: top, second, third, fourth, and reverse. The fence for sewing can be slid in. It can also be tipped over to cut a cant for V'ing. This knife here is very, very important, because otherwise, when the table's coming back, if a piece of wood gets on the table, if that knife wasn't there, it would get hitched up in the teeth and carried over the bench. And on one occasion, I had a gate post, which is a 7x7 post, hitched in the saw, and it was carried right over the whole thing and crashed to the end of the shed in my sawmill. If you listen to the sound of the saw, because we get different gears, the first time I started, the governor told me to listen to the sound of the saw, and you'll know how fast to feed the log. Someone said to me here a couple of years ago on the field, "What's the difference in all these saw benches?" Well, I said, they all do one job. But I said, I like to think that the Stenner is the Rolls Royce, because once you've worked on a Stenner, everything else seems a bit different.
Throughout the first part of the 1900s, the steam traction engine became a power for many uses. Its power was used so productively that there was a changing picture of production both in agriculture and also in industry. This new and increased production meant there was more demand on the roads and also on the existing transportation. Roads were being built throughout Britain, and whilst this new power of steam was producing this extra productivity, steam rollers began to play a major role in road construction. A fine collection of steam rollers have been beautifully preserved by many British steam enthusiasts, continuing the story of steam power and the part it played in the construction of many thousands of miles of roads that were built at that time throughout Britain. The heavy haulage demonstration at the Great Dorset Steam Fair each year shows the power and the ability of this new form of road haulage.
So there we've got one for forming around the ring during the latter part of this year, and then after the season he will be going over the Holland. He's got more courage than I have, Jerry. I fought very shy at times.
I would like to give this big wheel at the back there, David. I think this is one of the differences between the burrows and the fowlers. I'm sure the fowler enthusiast would insist that John Fowler was an engineer and he knew what he was doing when it comes to a compound engine. You use the steam twice. You put it in the high pressure cylinder first of all, and then the exhaust from that is used in a low pressure cylinder, and by the time it's gone through. But of course this year is the 50th anniversary of D-Day.
Hauling more modest loads, the steam wagon became a common source of moving goods of all descriptions. Unlike in North America, where petrol had become so abundant, in Britain coal was still the fuel of choice for many of the wagons that travelled the roads of Britain in the early part of the 1900s. The names of Foden and Sentinel were the most popular of these steam wagons, and were mostly built in the 1920s and 30s. The earliest of these wagons were slow and fairly cumbersome, but the latter engines became remarkably sophisticated, managing speeds of up to 60 miles an hour. Each year, the travelling fairs pulled into the villages and towns all over the British Isles. The colour, the brightness, and the sounds of these fairs were such a part of the summer, a time of great expectation for everyone. For myself, the sounds of the fairground organs still bring back many of the memories of those summer evenings of my childhood. Most of these wonderful organs were built in Belgium and in Germany at the end of the 19th century, and into the early years of this century. The craftsmanship that combines today's engineers and the British steam enthusiast has created a marvel of miniature engines that would be hard to compare anywhere in the world. Working demonstrations of these scale models were set up throughout the site at the Great Dorset Steam Fair. Many hundreds of hours of work go into the completion of these working engines and machinery.
The engine I built in 1986, finished, it took 3 years to build. It's built from casting on the market to be able to buy the casting to machine up myself. You want a thrashing machine. The engine is built 4 inches to the foot, which is third size, full size, and the thrashing machine is built to take to go with it. I've been working on the thrashing machine now for 3 years. It's not completed yet. Quite a bit more to do to it. It does thrash at the moment.
Right, 4.5-inch scale barrel traction engine, built by myself in 1982. Built it from the original drawings. It took me 6 years to make as part-time hobby. It's at a full 5-ton, just a traction engine on its own, and all the bits I've made myself. The castings I had done at the foundry in Poole. The wheels I built myself. It's quite an expensive little hobby today. It costs about £3,500 for the parts. But it's a worthwhile hobby doing. You start off first with your boiler, which must be steam material in order to build a boiler. It must be classified with a certificate for steam boilers. You built the boiler first, and the next thing you do is the horn plates which carries the gears, which you have to get, you machine them yourself on a milling machine. Once you've done that, you start fixing your main bearings. You get your crankshaft cast. As a cast, then you turn them up on the lathe, get the crankshaft down, you make your eccentrics, your main bearings, the flywheel's cast on the pattern we do ourselves. And once that's done, you start assembling parts together on the horn plate. Then you make the back piece, which is the tender, which carries the coal and water. And where the driver normally sits, it carries 4.5 gallons of water in the tender. and it's done by a mechanical pump which is here, which feeds the boiler all the time. And if that goes wrong, on this side here you've got an injector which pumps 8.5 pints of water per minute. Keep the water up on the halfway up in the glass, and we run at 110 pounds pressure all the time. Every year we have a boiler inspection where 2 engineers come down to my workshop, and we have about 10 engines lined up, and we all do inspection of one another's engines. And it's hydraulic tested at 250 pounds per square inch on every boiler and hold for 20 minutes. Once that is done, the full inspection of the boiler is carried out. All steam joints, every joint is inspected to see that it doesn't leak steam. Once that's done, you get a boiler certificate. But when you first start off, you have boiler test and you have a steam test afterwards. The steam test is just to check that the safety valve, which is up in the front, the safety valve lifts at 110 on pressure. When it's 110, it will lift up and let the steam out so it doesn't go over the top. Now inside the boiler, for a safety margin, we have a plug which is about a ½ inch size, and it's got an 8-hole drilled in the centre, and we fill it with soft solder. Now any time this engine runs out of water, this is filled up with lead, and the lead will melt and will automatically put the fire out. And that is a safety factor of your engine. That saves your boiler, it saves any explosion whatsoever.
These models are part of the afternoon display each day, as their owners and operators drive around the ring, giving a wonderful exhibition of these works of true craftsmanship. With the increased use of this new machinery, farmers were able to manage larger areas of crops. When the thrashing machine showed up in the late 1800s and early 1900s, there was a considerable change in the management of these ripe crops. It meant that crops could be harvested in the fields or in farmyards almost immediately after cutting. This machinery was greatly altering the ways that farmers were able to plan their year's work.
Hi, hello, I'm Brian Wilkins, and I've been coming now to the Dorset Steam Fair for 23 or 4 years. In fact, since I bought my engine, the Corn Maiden. Previous to that, I used to come down. I always used to find I was on the wrong side of the fence, and I thought there's only one way to be on the right side of the fence, and I must get an engine, so eventually I did. But we're not here to talk about my engine particularly at the moment. We're here to talk about the development of the thrashing machine, such as you see behind me. Thrashing started in the early days before the invention of machinery, when corn was grown in the ground and then harvested with a hand sickle and formed into sheaves tied together in bundles and taken to stone-built thrashing barns, of which there are still quite a number in this country. These barns were long buildings, long stone-built buildings, very high, and they were in the form of a cross, so that there was a long piece to the building and then a short cross piece. And in the short cross piece, either side of there were very tall doors. And they were so positioned so that the prevailing wind, if those doors were open, would blow through from one side to the other. And on the floor, in the centre of that cross, was a wooden floor. And when it came to separating the grain from the straw, they would take the sheaves of corn and put them on the wooden floor and beat them out on the floor, using, more than likely, a flail system to actually beat the grain out, so that you ended up with the straw and the chaff and the grain in another section. So the straw would be taken away, that would be used for bedding for the animals, but you then still had the grain and the chaff, which you needed to sort the grain out. So this was then separated by a machine that was then developed called a winnowing machine, which was basically a box with a fan on it, and you put the corn and the chaff in at the top, and it came down through a series of sieves. The fan blew, the sieves rattled, and the grain shook down through, and the fan blew the chaff out the other end. So you were left with the grain. A further development then from that was to do away with the flailing system, and the winnower was developed into a barn thrasher, where it was incorporated a drum and concave system, where the whole sheaf could be fed in, and the drum and the concave actually knocked the grain out of the sheaf. The straw then went on, the grain then went down through a similar system of sieves and fans and came out at the other end as grain. And that was in use for quite a long time, until such time as machines like this one were developed, and they were developed in the late 1800s. With the advent really of the binder, which came and could work in the fields and cut the corn into sheaves and cut it much faster than men could cut by hand and make a much neater job. And this meant that you could grow bigger acreages, and the corn could then be put into ricks and kept until such time as it could be thrashed out. So these machines were developed for that. They had a much greater capacity than the barn thrasher, but they worked on exactly the same system. You still had a fan, which is based here, which is driven through a series of belts, a big blower fan that blows air up through the machine, through a series of sieves. The corn is fed in at the top of the machine, beaten out in the drum and concave, the same as the barn thrasher, and then the straw and the chaff and the corn finds its way down through the machine through a various series of sieves until the long straw goes out at the top, the shorter straw goes out at the bottom at the end, and the corn finds its way eventually right down into the bottom. And then it's taken by an elevator up then to the top of the machine again at the end, at the back of the machine, and that then is the cleaning part of the machine, which is then similar or basically the same as the old winnowing machine that we had back in the old thrashing barns. And there's a small fan here, so you've got a supplementary fan to blow the fine dust and stuff out of the grain, and it eventually finds its way down into the back here, and right at the last process of the separation is a rotary screen, which is a cylinder with essentially a wire wound around it, which can be moved in and out from end to end, so that if you move it tightly together, you have very narrow gaps between the wire, and if you pull it out, you have wider gaps. So the idea is that at the one end you have a narrow gap, gradually getting wider until you get to the end. The purpose of that was that the big grain, the corn, being the biggest part of the process, would come through to the end and drop down there, so you had your good grain. The smaller seeds, right down to very fine seeds, which would be weed seeds and not needed, would come down to these other bags. And you'd have weed seeds in one, and then you'd have sort of tailings and fine corn in the other bags there. Nowadays, of course, the corn that we grow here is very clean because it's sprayed and it's treated, and you don't get any weeds growing in it hardly at all. So it starts off very clean. But when these machines were first developed, there weren't sprays like that, so the corn, when it was grown in the fields, you had the weeds growing with it as well. And of course, they would be bundled up in the sheaves, and of course, they would go through the thrasher as well. So you had to, at the end process, to separate the corn from the weed seeds as well, because they were thrashed out at the same time. So that really is the development of the machine. This is a machine made by Marshalls at Gainsborough in England. And this one was actually made in 1954, which was quite towards the end of the development of the thrashing machine. But the basic design didn't change. Once they settled on this design, this was the design that they kept to. And whatever make you look at, they'll all follow the basic same design. They varied a bit in detail, but basically they were the same design. And these were then used right up until the late 50s into the 60s, until really such time as the combine harvester was developed. And of course, once the combine was developed, that was the death of the thrashing machine. But there is a but here. There are still quite a number of houses thatched with wheat straw in this country. Now, to get the long straw, if you put it through a thrashing machine, the thrashing machine damages the straw. So the straw coming out of a thrashing machine would be no good to use for thatching straw. So another device was developed called a reed comber, which was a further piece of machinery that fitted on top of the thrashing machine. And what that did basically was to go ahead of the drum and concave. And that basically, the comber would take off the corn, thrash the corn out by large rollers with big teeth on that go around and actually comb the corn out of the straw, but doesn't damage the straw. The straw then goes off at the back of the machine and is still long and straight. And that then is bundled up into bundles of reed, and that then forms the reed for thatching. The corn that then is thrashed out goes down through the machine exactly the same and ends up down here. But there's been no improvement on that system since that was developed back in the late 1800s, early 1900s, and that is the way that the thatching reed is still made today and never been improved on, which is surprising really, but whoever designed and built the thrashing machines originally obviously got it right. So we've got the main fan here then that provides the main source of air for the machine to blow the dust and the chaff out. Now, you get various byproducts from the machine, including the long straw, the short straw, and the chaff that comes out here. Now, when the machine was first developed, the chaff would simply come out onto the floor, rather as you see it here in a great heap. And of course, you needed quite a lot of men to run a thrashing machine. You needed men on the sacks, feeding the machine, putting the sheaves up from the rick, and clearing away all the debris from the machine. So to economize our labor to an extent, the later machines had things like this blower put on, which would take the chaff and blow it up through a pipe up here, and you could put an extension pipe on as long as you wanted to blow it away into a heap somewhere clear of the machine. So that was a development towards the end. This being a later machine, of course, it has got a chaff blower on it. The long straw, when it comes out here, generally is baled up for use as a stock litter during the winter. This is a Powell stationary baler. It's built in Liverpool, and the straw comes off through the straw walkers from the top of the machine down into the hopper on the baler. This nodding donkey, as we call it, comes down and presses the straw into the chamber. There's a ram here that goes to and fro, compresses the straw into bales, and in fact now is tied with string. But these particular machines were designed to be wire tied, and you actually had wire that came through and then was looped together. But now most of these machines that are used now have been converted to string, and that seems to work quite adequately well. The setup that we've got here at the moment, we've got the baler right up behind the thrasher, which again saves the straw coming onto the ground and the man having to fork it up into the baler. We're able to do that because we're driving the baler and the thrasher with the traction engine at the other end. The traction engine drives the thrasher, and then there's a belt from the thrasher that drives the baler, so the whole thing all works as one big unit. The traction engine itself is a Ruston Proctor traction engine, a 5 nominal horsepower engine, built in 1918, and itself was a thrashing engine in Herefordshire up until 1951, owned by one man from 1920. The engine was built in 1918, but it wasn't used. It was built for the War Office and was sold in the War Department sale and bought by Charles James and taken to Penny Park in Herefordshire, and he used it in his thrashing business. So it's a typical agricultural engine, a typical thrashing engine, only 5 nominal horsepower, but able to drive the thrashing drum and the baler as well, and cope with it quite adequately well. The traction engine, which incidentally is called the Corn Maiden, a very apt name for an engine that drives a thrashing set, is a 5 nominal horsepower engine, but that bears no relationship to the actual horsepower. The actual horsepower of this particular engine is 24. And that's developed at very low revolution. So a steam engine is a very torquey engine, as we say, develops the speed very low down, the power very low down, and is able consequently to drive the outfit like you see here today. The nominal horsepower part of it, there is a formula for working it out which relates to the piston size and the stroke size, but it originally developed when the engines were not self-moving as this one is, but they were termed portable engines. And that means that they were exactly the same as this, except that they were on 4 wheels and they weren't able to move themselves about. To be able to move them from farm to farm, they were then horse-drawn, or even pulled with oxen or mules, but horse-drawn generally in this country. And depending on the size and power of the engine, the more powerful the engine, the bigger it was, the heavier it was. So it needed a number of horses to pull it about, which might have been 4, 5, 6, 7 or 8 horses. So that was where the rough nominal horsepower idea came about, that it was determined by the number of horses needed to pull the engine about. And that, as far as I know, is the origin of nominal horsepower.
Many of the thrashing crews on the prairies travelled from one farm to another. Large crews of as many as 25 men worked from early morning to late in the evening, loading wagons, feeding the separator and running the engine. One of the most popular makes of separators used for thrashing the prairie crop in the earlier days was the case. At first, just as with the separators in Britain, many of these thrashing machines were made out of wood. But by the first years of the 1900s, these wooden separators were being replaced by the first of the galvanized steel machines. These case separators were built in Wisconsin and came in differing sizes and capacities up to the larger 4466, requiring one of the larger steam engines, producing as much as 75 horsepower on the belt, to run them. Although the case separators were the most common, other makes were also available. The Altman-Taylor thrashing machine was sold by the International Harvester Company in Canada in the early parts of the 1900s. International then went on to build their own machines in the 1920s and 1930s. Nichols and Shepard, the farm machinery manufacturer from Battle Creek, Michigan, built another popular machine called the Red River Special, while Sawyer Massey produced one of the more popular Canadian-made machines. The use of these separators carried on through the war years of the 1940s, with a few still operating into the 1950s.
The engine that we're going to thrash with today is a 75 horse George White, and it was found up in near the Riding Mountain, and Frank May owned it, and now it's been here. I think their family still own that engine, and it's been on this museum grounds here for maybe 10, 15 years. Garth Crooks is running it, and it's a rear mount. And the rear mount is, the back axle is behind the boiler, designed for plowing. And today we're going to use it for thrashing, and you'll have no trouble driving it.
Small barn thrashers also found a place on some of the smaller farms throughout Canada, whilst a similar design was used in Britain, which was called the Crofter's Thrasher. These machines were quite economical to buy and were easily run by some of the smaller stationary engines that had become available at this time.
My grandfather bought a separator, Stanley Jones separator, in 1906, and it got destroyed in a fire probably about 40 years ago. So my uncle, who's 85 this year, he found this one, and because he had remembered running it and whatnot, then he started restoring the separator. But we needed a motor for it, so we dragged that one out of the boneyard here, and I rebuilt the motor on it. So between the two of us, we've got it up and going. Okay, well the motor itself, it's a 5-horse Fairbanks Morse, Type Z, built around 1923, somewhere in that area. Fairbanks made more motors for eons and eons, but it's one of the later ones that they made. These engines, 5 horses, was about the maximum you could use, or the minimum you could use on this separator. If you had a blower on it, then you had to go up to about a 10 horse on this separator. So that motor is just about right for the separator the way it is. This particular separator would have been used mostly by farmers that, just small farmers. This was a barn separator, would have gone up in the loft, and they could start the engine up on a cold, miserable day when it was too miserable for anything else, and thrash and just run the grain right down into the lower level of the barn. It wasn't actually designed to be on wheels and hauled out to a field. It was just made to be parked in one spot and bring the grain to it. About the same era as this machine, T. Eaton and Company was selling through their mail order catalogs the Eaton engine, anywhere from 4 horse up to 12. Anywhere from a 5 to a 7 horse would have run this machine just the way it is. Those engines sold around that time for delivered to Winnipeg for about $195. And but the Fairbanks was a fairly popular engine at that time. It could have been a Fairbanks. Anything that was throttle governed would have run this machine fairly well. Hit and miss engine wouldn't have made it.
And so it was a time of great change in agriculture. The enormous ability of the prairie grain basket and the hard work of the pioneers that had settled the West managed to absorb these changes quite easily. As the pioneers moved across the West, they brought with them many of the ideas that they had known in their own farming areas from where they originated. Although many of these pioneers were from Europe, some came out from central Canada. One of the finest examples of a small farm museum has to be the Motherwell farm at Abernethy in Saskatchewan. Mr. Motherwell was a well-known figure and a very progressive farmer, bringing with him from Ontario many of the ideas and practices that he had known and learnt when he was growing up. The development of the Motherwell farmstead was one of diversity and forward thinking. At a time when many farmers were turning to steam, Mr. Motherwell decided to experiment with a hot power gasoline and kerosene tractor.
This is it's called the Motherwell Homestead National Historic Site, but it's not quite right because the buildings we have here, there's an elaborate stone house, very large barn, very expensive stuff. It's not actual what Motherwell came out and homesteaded with. He started off in a log cabin and a small log stable. And this is the after effects of 30 years of hard work out on the prairies, tilling the land and making himself more successful, becoming more successful. So he started out in this log cabin. He lived in there for quite a few years. For about 13 years he gathered rocks, and then he built the stone stable of the barn here. And then he went ahead the next year and built the house. Of course, your animals, getting shelter for them was more important than the house. So he built that first. Then he built the big fancy stone house, and they moved over here, and he acquired more land over the years. He ended up with 960 acres, which was quite a considerable farm for that time period. And then in 1913, his son married, and he gave his son 2/4 of land. And then the size of the farm there, of course, decreased. The son started the farm up there. The father wasn't out here as often because he was in Regina with Parliament, being Minister of Agriculture for the first Saskatchewan government. So things sort of started deteriorating here around that time period. We depict the year 1912. Mr. Motherwell was basically a grain farmer. He had pigs, chickens, sheep, all the livestock, but all of that was simply to be self-sufficient. Also, his gardens were very large, and that was also to contribute to self-sufficiency. Basically, they didn't want to have to depend on the towns. So they had very large vegetable garden. They summer followed half of it. Half was planted, half was summer followed, and then they'd switch sides the next year. So they were always ensured plenty of moisture to provide a good crop. They also had a separate garden that was simply for potatoes. Potatoes were a very important part of their diet. So basically everything they could do to be self-sufficient out here was done. The livestock was sometimes sold. If they had had a crop failure or something like that, they might sell a few pigs or that to bring in a little extra money, but generally they tried to be as self-sufficient as possible. Mr. Motherwell's farmyard here was actually an example from Ontario. If you would travel out to Ontario, you would see basically the same type of stuff. Mr. Motherwell came from Perth, Ontario, moved out here in 1882, and he transported all his ideals and beliefs out here. The styling of the house is very similar to what you'd see in Ontario. The barn is taken right from Ontario. It has the vertical siding, the ramp up into the loft to take the hay up there. All the trees planted around here. When he first came out, there was no trees, and all of these were planted, very organized. He divided the homestead up into quadrants so that everything was well organized and everything had its place. There's the barn quadrant, the dugout quadrant, garden, and then the house, each serving their own purpose, and divided up so that, for example, the house is divided from the barn quadrant with a big row of trees, so guests out here wouldn't be able to see the animals and stuff in the barnyard. Mr. Motherwell came out here, he started breaking the land with horses. He was quite fortunate he came out and he acquired horses very early. He was a firm believer in the saying that it is impossible for a man to remain Christian and farm with oxen. So he acquired horses very early and broke his land for many, many years. He was a great lover of farming with horses. He wasn't a fan of mechanized agriculture. But in 1911 he did purchase the Hartpar tractor and also a gang plow to go along with it. Being Minister of Agriculture, he was trying to set an example. Now this example was set in that he had purchased the stuff, but he actually didn't run it himself. He sent his son to school in Saskatoon at the University of Saskatchewan to learn how to run the tractor, and I don't think Mr. Motherwell ever set foot on the tractor. He was not a big fan of the new techniques. So the steamers were out in the prairies here around the 1890s. Motherwell relied on other farmers in the area to do his threshing with the steam tractors. There was a group of brothers, the Stuke brothers in the area, that generally did most of the threshing in this area, and they had purchased the steamer very early. So Mr. Motherwell wasn't really a leader in all aspects of purchasing tractors and steamers quite early, but he tried to also set an example himself. The Hartpar tractor that Mr. Motherwell purchased in 1911 cost him $535, which was a considerable investment at that time period, but Mr. Motherwell thought it to be a good investment. The Hartpar company was very well noted, based in Charles City, Iowa. They developed one of the first kerosene engines in 1901, and then this tractor was a forerunner from that, or a predecessor from that, I guess you'd say. Very, very well noted, one of the most famous tractors of the time, I would have to say. It was nicknamed Old Reliable due to its reliability, and it was also very easy to operate. The controls are quite simple. It replaced the steamer in so many ways, you can't describe them all. The steamers require 3 hours of fuel, wood or coal, whatever you're using, just to heat the water up to get it ready. This tractor here, you start it in about 15 minutes, it's running, you can head out and start working right away. Doesn't require all the wasted energy just to get it running. It works good on hills. It requires quite little fuel. It would use about 60 gallons of fuel a day, which was not bad fuel consumption for back then. You didn't require as many men. A steamer requires one man to operate, a skilled man with his boiler ticket, also a man hauling wood and a man hauling water also. The Hartpar tractor here could basically be run by one man. You'd fuel it up in the morning, you'd start it up, and you could work all day on that one tank of fuel. So it was a very good replacement for the steam tractors of the time. It was also comparable in power. This Hartpar tractor here is rated at 3060 horsepower, 60 on the pulley and 30 on the drawbar, which was quite considerable horsepower for the time. It wasn't as powerful as some of the large steamers, but quite comparable with the more common smaller steamers. Okay, I guess we'll start at the back of the tractor here. You look at the fuel tank and it's very interesting. It says for gasoline on the top, and then the large tank is for kerosene. Now the gasoline tank was very small. It was simply used to start the tractor. The kerosene wasn't volatile enough to actually get the tractor started, so they used the more expensive gasoline to get it running, warmed it up for about 2 hours, or it would take about 2 hours to warm it up, and you would switch to kerosene. The tractor would be able to work under the gasoline, but you switched to kerosene because kerosene was a lot cheaper. The gasoline was it was expensive, it was hard to get a hold of. Kerosene was readily available, so that is why the tractor was made to run on kerosene. It was very good fuel for the time. It's kind of interesting now, kerosene is a lot more expensive nowadays. We simply run the tractor here at the Motherwell on gasoline with a little bit of oil mixed in it. When you're running on kerosene, up at the front here, there's this big silver tank, and that tank was for water. You did use water with this tractor, except it was simply a small amount mixed in. It made the kerosene the kerosene engine run better. It prevented pounding and poor running. It sort of cooled the kerosene and prevented it from pre-igniting. So they had the water tank up here, the gas tanks at the back. Sort of interesting placement of the water tank over top of the engine. The water would be very warm, so it would evaporate quite readily from the carburetor when it was being injected into the engine. Another very predominant thing on the tractor here is this flywheel. The tractor originally operated on a hit and miss system where it would fire a few times till it got up to speed, which was about 300 RPM. Then the governor would kick out and it would coast, and this flywheel here would keep the momentum going. And then once the tractor lost momentum, once the RPMs decreased to a certain amount, the governor would kick in again, and then it would start firing again. It would fire till it got up to its speed and the governor kicked out, and it would keep running like that. Now under a heavy load, basically it would be firing all the time. If you're just driving the tractor, say moving to a field or something, it doesn't fire all the time. And it doesn't run that rough. With the big flywheel here, the flywheel weighs 1,000 pounds, there's a lot of momentum, so the tractor runs very smooth. It's not a jerky like you would think with the hit and miss. It's also the starter here. To start the tractor, you simply get on the flywheel and you have to spin it around. It's quite a chore to spin it around. You can imagine trying to get all the momentum up. We can also look into the engine here. Very well designed according to Art Parr. Very simple to do engine repairs because you open up the end of the crankcase here. You have the crank right there. You have the connector rod. You can pull it right out, and you can also see right in. You can see the cylinders. When we first start the tractor up, what we do is we open this up and we check to make sure it's being properly oiled. The lubrication system on this tractor is something. The oil is simply used once. It's a drip system. The oil drips onto the different places in the engine and collects in the bottom of the crankcase here. And as you can see, there's quite a fair bit of oil on here. The oil simply splashes out and is used up, and so you just have to keep filling it up with oil. There's no oil changes like on a modern day tractor. So very easy to do any engine repairs here. One of the Art Parr's selling points that they used at the time. You can see right on the front of the crankcase here, the Art Parr plaque. Art Parr Company, Charles City, Iowa, engine number 5013, patented December 15th, 1903, November 15th, 1904. Other patents pending. The Art Parr Company formed in 1901 with the design of their first tractor. This one was designed very shortly after, and it was basically their benchmark. The most popular tractor they designed, they didn't change the design for very many years. They kept with the same design because it was so well noted. It was very reliable, and there wasn't many changes necessary. Another predominant feature of the tractor here is the radiator at the front here. It's filled with 110 gallons of oil. The Art Parr Company used oil for cooling. Their selling point on that was the fact that oil didn't freeze during the wintertime. So in the wintertime, you wouldn't have to worry about draining the engine and that every night when you shut it down. Of course, if you're using a water-cooled engine and you're threshing in the fall, you'd have to drain the engine every night, which would have been quite a chore. So the Art Parr Company chose oil for their cooling system. The rad here contains 110 gallons of oil. There is a pump that circulates it all through the engine. The cooling is quite interesting. You can see the big smokestack at the top there. Now what happens is the exhaust comes up to the front here, and then it fires up that tube. And what happens is that causes a suction in through the rad here. So the air is sucked up in through the rad and out the top along with the exhaust gases. So it's not a great force that's drawing the air through there. You can hardly feel the suction, but it does keep the engine running quite cool. The oil here, there's such a mass of it, it takes about 3 hours of operating till it gets warm where you can't touch the radiator. You run it for 2 hours under a pretty good load and you touch the engine or the rad and it's not even that hot yet. We'll come around to this side here. This is where everything happens. This is the pulley here for powering the threshing machine or whatever else you decided to power with it. It's also the clutch, the gears, everything happens right here. This is also where you find out how dangerous these machines were. You can see this key right here. In this upward position here, when you engage the clutch, all it does is spin the pulley. Now once the tractor is running and you want to drive it somewhere, what you'll have to do is you'll have to come down here, align it with a special notch inside here, and then you have to click it in place. Now that doesn't sound too bad, except for the fact that this plate right here, and all these gears, they're all spinning inside. So you're working about 2-3 inches away from moving parts. You have to make sure you have no baggy clothing or anything like that. Very easy to get caught up. So that's basically how it runs. It has 2 clutches on it. You can see the clutch plates in here. They engage on this flat surface here, and then that's where you get your forward. To get reverse is totally opposite. It's right back here. These 2 plates clamp on this plate right here, and then it uses the planetary gears and you get reverse. This tractor is quite easy to start due to a few innovations made by Hart Parr, and some of the other tractor companies also had these innovations of the time. Right here we have decompression valves, very simple. Just pipe with the valve screwed into the cylinder. There's one for each cylinder. This is a 2-cylinder motor. So there's one for each cylinder. You open those up, and we also have priming cups. You take the lids off the brass priming cups here. One on this side for this cylinder, and one on this side. So you remove them, you fill them up with raw gasoline, and then you dump them in the cylinder, and then that helps you start the motor. That gives that extra boost to get it going right off the start. It's very interesting operating this tractor. It basically is like running 2 separate motors, because you have one cylinder and you have the other cylinder, and the controls for each cylinder are separate. So you have to watch the smoke, watch the exhaust, and determine which cylinder isn't pulling its weight, which cylinder isn't operating properly, and you have to adjust each one individually. So basically you're running 2 engines at once. So when you start the tractor here, you open up your gas line, and then you check down the line here. You can check to see if gas is coming out here. Then you come over and make sure the float is risen. So you open this petcock here, and then you just tap the float and make sure the gas is coming out. Then you can close that petcock off. You can see there's 2 bowls in here. This back one is for the fuel, and then there's the front one for the water. Like I said, you run water in with the kerosene to help it run a little better. So there's the separate carburetor for the water, separate carburetor for the fuel, and then there's all the separate controls. These are the cylinder, the mixture controls, mixture of the fuel. There's one for each cylinder. So you adjust them according to how the tractor's running, if you need more gas or more air. And there's also your throttle controls. You can see this is the throttle for the gasoline. There's the water mixture controls in the front there. So you have to really know how to run an engine. For some, you can imagine switching from horses to something like this tractor, where there's all these adjustments to be made and you're not really sure how to make them. It took quite a considerable bit of education to learn how to operate the tractor. And you also had to learn your tractor. Every tractor operated a little differently. So you learn where to set it to start it, where to set it to run it, and you get to know the tractor quite well. There's the throttle controls up here. There's also timing. You have to set the timing accordingly to how the engine's running. So when you start it, of course, you set it right back so that it doesn't backfire. Again, there's controls for each cylinder. So you start off with it right back, and then once the engine's running, you advance it till where the engine is operating at its peak efficiency and power.
I wonder whether any period of farming will ever see such change as was experienced in the latter years of the 1800s and the early 1900s. The great adventures of the North American pioneers, the opening up of the vast acres in Western Canada and the grain belt of the northern United States, and the transformation of the power that worked these lands from the horses and oxen to the large machinery that we now consider with such interest. It was surely a time of changing ways in farming.